Every time you pick up your phone or sit down at your computer, you're interacting with something truly incredible. It's this piece of software that's so fundamental, so powerful, that most of the time you don't even notice it's there. It's the operating system, and it's the invisible foundation for pretty much everything we do in the digital world. So let's really get into what it is and how it works. Think about it for a second. You press a button, and this lifeless box of electronics just springs to life. Suddenly there are icons, windows, all your apps ready to go. But how? What actually happens in those first few moments to take a computer from, well, basically knowing nothing to being ready for you to log in?
To really appreciate what the operating system does, we have to start by understanding the problem it solves. And to do that, we need to look at a computer in its most basic state, what engineers call bare metal. It's here we see why an OS isn't just helpful, it's absolutely essential.
So picture a computer with just its hardware. You got the processor, the memory, a hard drive, and that's it. This is a bare metal system. This is a pile of very sophisticated electronics, right? It has all this potential, but absolutely no instructions on what to do with it.
Okay, so the very instant you give it power, the CPU, the brain of the operation, wakes up, and its only purpose in life is to follow instructions. So it immediately looks to the system's memory, the RAM, for its first command. But here's the catch. RAM is volatile. That means when the power was off, it forgot everything. All that's in there is random electrical noise, basically garbage. The CPU tries to read that garbage as an instruction, and it crashes instantly. That right there is the bare metal problem.
So, how does a machine get around this? How does it pull itself up from nothing? The answer is this really clever step-by-step process. You can think of it like a ladder that the computer climbs rung by rung to go from a state of total ignorance to being fully up and running.
This whole process is called the booting up, and it really comes down to these 4 key steps. First, obviously, the power comes on. Then, a special little program called the BIOS starts running. That BIOS then finds a tiny program on your storage drive. And finally, that tiny program is what loads the kernel, the very heart of the operating system, into memory.
So the solution to that garbage in memory problem is a different kind of memory, one that doesn't forget. The computer's very first instructions are physically etched onto a read-only memory chip, or ROM. This program is the BIOS, and its first job is to do a quick health check, a power-on self-test, just to make sure all the essential hardware, like the RAM, is actually there and working.
Right, once the BIOS confirms the hardware is good to go, it has to find your storage drive. But it hits another snag. See, there are all these different ways to format a drive, different file systems. The BIOS can't possibly know how to read all of them, so it does something smart. It looks for a very specific, very small piece of the drive called the boot sector. And in that sector is a tiny program whose only job is to tell the computer how to read the rest of that specific drive. It's like the key to the whole system.
Okay, so with those instructions from the boot sector, the computer can finally find and load the most critical part of the operating system into RAM. This is the kernel. And as soon as the kernel takes charge, the computer really comes to life. Now the real work can begin.
You can think of the kernel as the conductor of an orchestra, or maybe the CEO of the whole computer. It decides who gets to use the hardware and when. It manages how all the memory gets divvied up, it allocates precious CPU time to all the different programs, and crucially, it handles errors, so one bad app doesn't bring down the whole system.
Let's dig into one of the kernel's biggest jobs, managing the hardware. Just imagine for a second what it would be like if every single application, your web browser, your games, everything, had to be programmed specifically for every single brand of graphics card or every type of printer out there. It would be total chaos. It would be impossible to write software.
So the operating system solves this with a really powerful idea called abstraction. And this quote explains it perfectly. When you press a doorbell, all you do is press the button. You don't know or care if it's hitting a physical chime or sending a signal to a smart speaker. The button is a simple, standard interface. The OS provides that same kind of simple interface for software. And the difference is just night and day. Without this abstraction layer, software is incredibly complex and fragile. Any new piece of hardware could break it. But with the OS handling things, an app just has to make a simple request like, hey, draw a circle on the screen. The OS then takes that simple request and translates it into the complicated, specific instructions that the particular graphics card needs. It makes everything simpler, stronger, and able to work with new hardware down the line. But managing hardware is only half the story. The OS is also this master juggler of software.
Right now, on your computer, there are probably hundreds of different programs or processes all running at the same time. And inside each of those are even smaller subtasks called threads. It's the kernel's job to act as the taskmaster and keep all of this from descending into chaos.
So how can a computer with, say, 8 processing cores run hundreds of things at once? Well, the trick is something called task switching. The OS is constantly and rapidly switching between all these different tasks, giving each one a tiny, tiny slice of the CPU's attention. This happens so fast, we're talking thousands of times a second, that for us it creates this perfect illusion that everything is happening at the exact same time.
And the scale of this is just staggering. Get this, a single core background process, the kernel task itself, can be juggling something like 149 of these different threads on its own. We're talking about everything from managing your network connection to the little autosave feature in a document. Most of these things are just sitting there, waiting, but the OS has to be ready for any one of them to need something at any millisecond.
So we've looked deep inside at how an OS works. But it's also really important to remember that not all operating systems are created equal. Different jobs require different tools, and that's led to a whole world of specialized operating systems out there.
You've got your general-purpose systems like Windows, macOS, and Linux that are designed to do a little bit of everything on our desktops and servers. Then you have mobile OSs like Android and iOS, which are completely optimized for things like touchscreens and getting the most out of a tiny battery. And then there's this other fascinating category, real-time operating systems. These are for things where timing is absolutely critical, like in a car's anti-lock braking system, where a command has to execute within a guaranteed, precise window of time. No delays allowed.
All right, so let's bring this all home. We've gone all the way from a dead piece of hardware to a fully functioning multitasking machine. And it's all because of this complex, beautiful chain of events orchestrated by this invisible foundation we call the operating system. When you really boil it down, the operating system is the ultimate translator. It's the essential bridge. It solves that impossible bare metal problem with the boot sequence. It tames the wild complexity of hardware with abstraction. And it acts as the master conductor for all our software. It truly is the fundamental layer that makes modern computing even possible.
And that kind of leaves us with one last big question to think about. We've seen operating systems evolve from giant mainframes to the supercomputers in our pockets. Now, as they get embedded into literally everything, our cars, our appliances, our homes, what new challenges will they face? What will the operating system of the future even need to be?